Welcome to MACSMIN 2025. Now, Dr. Miloslav Torda will talk about how to go from molecular shape to crystal symmetry. Over to you, Mila, please.
Thank you, Vitaly. Thank you for inviting me to this new exciting stuff. Some parts I put together on Tuesday early morning, yesterday. I'm a postdoc at the Liverpool Research Center here. Although I'm not a chemist, I'm learning chemistry. So my background is computer science, and my job is to help chemists to solve their computational problems. So the title is a bit misleading. So it should be actually like this. So I didn't want to have like three lines of a title. So I tried to make it shorter. And so yeah, one common thing about hexagons and cuboctahedral are Radially equilateral. Or the view of friends. I'm going to go over the second part, but I realize it's too much. So the topic should be speaking of cuboctahedral molecules. So the first part I'm going to skip. If someone is interested, it's written up on my website in my research book. So there are some like animations. And it connects to the more interesting three-dimensional case. So a big part of my work is trying to understand the relationship between lattice energy and sphere packing. So Graham on Monday mentioned that this relationship is known for a long time, which is true, but even now, so this is take the opportunity to quote from 2015 European Mathematical Society review on the crystallization and the link with sphere packings. And so even now the problem is not in 2 dimensions is not completely understood, and in 3 dimensions it's completely open. So yeah, there's still don't know much. We don't know about this say called duality between lattice energy minima and taking maximum. So and another thing is that the review paper takes into account only monoatomic systems. So we are jumping straight into multi-atomic systems, which will be fun. So this is our model molecule. So for us, molecule is a rigid collection of hard spheres, like the one on the right. This is an abstract thing. I haven't actually found anything that looks even closely similar to this. So we have a collection of spheres with equal spheres on a regular cuboctahedral. So then we ask, what is the densest packing of such collection of spheres? So I try to guess. So yeah, I tried to guess. So on my last birthday, my wife gave me a present. So this toy, it's called the Yamak. I brought it here with me. So it's basically rods with magnets on one side and poles connected to each other, and one can make. So I was quite surprised, and one can actually make Euclidean geometry with this. So yeah, this is my guess at how would such a packing configuration work or look like. So yeah, this is one possible candidate, but is it the densest possible? So I'll leave you wondering for a while, or we can make a vote. This is the densest, I think. We'll find out, I think. So we also heard the strategy divide and conquer on Monday. So I use that, and it's maybe simpler to start with simpler molecules like tetrahedra or octahedra. So the tetrahedra and octahedra are connected with the cuboctahedron via the tetrahedral octahedral honeycomb. So the visualization is a sort of cuboctahedron, but half of the octahedra taken out. And when this thing assembles on in the framework on the right, so you can see that the tetrahedra building blocks are tetrahedra, and the voids are octahedra filling the space like this. So we have a decomposition of octahedral packing into tetrahedral and octahedral. How do these pack? So I tried to guess again. This was more successful. So these are Gelmach models of right tetrahedral molecules on the left tetrahedra, on the right octahedra. So the colors are okay. I will mention it later. So now again, is this are these optimal configurations, optimal packings of these kind of molecules? So the answer is yes. So if this is the face-centered cubic lattice, which we know is the densest packing possible. So every ball of this structure has 12 maximum of 12 neighbors, which is the kissing number of every ball. So and if the tetrahedra are connected in the lattice like this, every ball is covered exactly once by one tetrahedron. So yeah, we have covering of tetrahedra and basically a sphere packing. So yeah, this could be this is the optimal. Similar, it's in the octahedra case. Yeah. So we got the faces cubic glasses packing of spheres. The old Kepler conjecture, which was proved by Thales 400 years later. So yeah, we know the optimum. So we try to numerically verify it. So we have a packing algorithm built. It's a modified version of the packing algorithm we published in SCIEM, Journal of Scientific Computing. So this is an example. Just want to run quick through this. So in chemistry, one visualization when one works with visualizing electronic structures, molecular structures, is the space filling visualization style. So it's just a collection of spheres, and with the radii are given by the envelope radii. So yeah, we have an optimization algorithm built. Basically, it's not non-convex nonlinear. So yeah, the packing is the non-convex nonlinear optimization problem, which is one of the worst you can get. So we solve it via the modified version of the packing. It's an information geometry based global search method. So at the beginning of the animation, basically sampling. So we fix a space group. In this case, it's the space group P21. And at the beginning, we sample the whole space group, and hundreds of so every point on the scatter plot is one sample. So then, the algorithm or the method move into the direction of the best samples. So it's a version of it's a non-Euclidean gradient minimization over a space of probability distributions. So it's going into directions where the mean is the minimal. With hope, we get probability distribution of a delta function, so a point distribution pointing on the delta. So yeah, we have a way to run numerical experiments for these kind of molecular systems, even a space group. So this is a big part. We have to fix the space group, and the algorithm searches over the space group's isomorphism class. Yeah. So, and we get, and we hope to get. So, yeah, no guarantees. We hope to get the best densest stacking, but all right. So then we have the algorithm, but still, what kind of symmetries? So which we need to pick the space group for this. So from the models, one of the symmetries is the inversion. So there are the octahedra and tetrahedra are of two colors, blue and green. So these blue and green are related to each other via an inversion. So there is an inversion also in the octahedra case, but the octahedra have an inversion embedded in themselves, so it's not visible. And then we have lattice translations, which are the tetrahedra octahedra with the same color, are related to each other with lattice translations. So we have two symmetry operations. The smallest group having these symmetry operations is the P bar 1. So yeah, we run the experiments on in P1 in the P1 group for octahedral and tetrahedral. So these are the output structures. So yeah, we have the one on the right. It's actually the packing we got. The first two columns of images. It's don't visualize what's there's. It's only a collection of spheres. I mean, it looks good, it makes sense, but what is the density? Actual number. So the formula we use for packing is let's go through this. So volume U is the volume of the unit cell, and so for the tetrahedral case, it was 2 to the 7. Well, it's not exactly. It was like 0.9999. So it's very high precision, but still you get numerics. So the volume of the molecular system, it's 4 times the volume of a sphere with the radius of square root 2. So we have every vertex of the tetrahedron as so we have 4 spheres, and the radius of the spheres is square root of 2. So the total volume is this number. Then the n in the formula, it's number of symmetry operations modulo lattice translations. So here we have 2, inversion and identity. And yes, so yeah, we put this together, we get the face-centered cubic close packing of equal spheres density. So, and we know we can, yeah, so this is the optimum. We can't get any better than this. So yeah, the algorithm found the optimal configurations. So next we ask, is this the only symmetry? So is this the, what if we fix the space group, I don't know, at M, 3M or anything? So what we're going to get? So yeah, what kind of additional packing symmetries are there? So for this, I had to I used the fibrifold space group notation. Here is another space group notation, but the one I won't find fond of, although I'm still learning. So what's a fibrifold? We have so yeah, plane groups. Start with plane groups. So for instance, these are circle packings. So the P1 circle packing is just lattice packing of disks. P2, I mean, in some sense they are the same, but there is a twofold rotational symmetry or inversion. So the inversions of in the P2, so the lattice points, the blue parallelogram in P1 is actually the center of twofold rotation, which in the P2 are the centers of the spheres. So if if we fold up the configuration by identifying its symmetry elements, we get surface. Which people called orbit manifolds. So orbifold. Orbifolds because they is the plane group folded by its orbit. So the P2 packing, so the configurations or the P2 space groups has, this is a picture from Conway's book, things. So this is a visualization of an orbifold for a P2 group. It's a sphere with 4 cone points, and the 4 cone points represent the 4 twofold center of symmetry, centers of rotation of twofold symmetries. So then, if you notice, like you have these layers of P2 orbifolds in these configurations, which are then coupled with in another direction. So this creates another structure. It's called, which is basically a fibered bundle, where the base space is an orbifold. In our case, in P bar 1, it's P2, or like the signature is 222, and the fiber is it's a circle. So yeah, we get the fibrifold representation of a space group, which for me is very it has some good properties. So there are basically a space group means choosing one of these. So there are 3 directions. One can do this. In a space group, one can choose these 3 directions. So for this group, all the 3 directions are the same. These directions represent special projections, symmetry projections in the crystallography table. So these are the projections for the octahedral and tetrahedral cases. So based on this, we compiled a list of. We did some work on plane group packings. So the densest pack for convex polygons, densest packings are P2, PG, and P2GG. So for the list of closed packed groups, we took all the combinations of these 3 groups. So the space groups that have these special projections, there are only 3. Then there are 2 other possible ones. So we got a list of 6 plane groups, which have possibly one of them, the cuboctahedral models, will be defensive. So yeah, I mean, we run through all the 6 space groups. So this is the octahedral cases. They have the same density of the sphere packing. The same for the octahedra. So they pack. So the symmetry is the high symmetry. For the octahedra packing, it was PBCA. And so for cuboctahedral models, it becomes more interesting. So there is variability there. So come back to the question if this is the densest stacking. Is the second densest stacking. So this symmetry is PBTA or P21T. So the densest packing was this the Gell-Mag model actually looks like this. So we have these two lines crossing each other of two tetrahedra. So this is really optimal. I mean, globally optimal without any symmetry. The answer is yes. So the density is actually 13th of close packing of spheres. So it is also a lattice packing of cuboctahedra, but if one the spheres that is missing one sphere for every cuboctahedron. So if you the red ones are complementary packing, which is exactly the ones the density the one sphere that's missing from the. So we have the optimum. So the vertices are basically on vertices of a dodecahedral, rhombic dodecahedron, which means we have locally densest packings on two levels. So one, we have maximizing the kissing number or the coordination number between atoms, like a single atom, but then also between molecules. So every molecule is so the rhombic dodecahedron. It's connected to 14 others molecules. So to conclude, this is by these space groups. So one thing is these groups are the most 6 of the most frequent ones in the Cambridge structural database, which makes about 82% of the structures. So if you remove C2C, that's they're all centrosymmetric. That's 75% of the CSD. So yeah, this is exactly. So this is a table from a book by Kitagorsky, so the Russian physicist, and he actually compiled a list of these. If you can see the groups we have selected are in his list. So, and he actually took the same approach. So he analyzed possible layers of plane groups, and then he imagined it on stacking on top of each other. But that was 1973, no computers, so yeah. Model. So there is looks like there is nothing we can add to it, but there is actually we can add one more column to the table, and that's so for molecules with tetrahedral symmetry, the densest possible packing is the P/1. So thank you for the attention. Andy Cooper and Telephone and Universal Research Center for supporting me. Some parts of this was also done with drones. And also I'd like to thank Vitaly and Graham because they were the ones who started me on this.
Okay, thank you, Mila. Yes.